Good evening, everyone. Good evening. Hope all is well. Hope everyone's doing all right. Everybody's doing great. Before we get started, on my end, did anybody have any questions or concerns? Anybody try anything, get stuck? Everybody good. All right. All right. Where did we leave off? Oh, we did the chain rule. Okay. So just a recap of the chain rule. We started here, 3.6 chain rule. Only did one problem in the chain rule, and just decided to pull off since we had already did some other things. But just to review the last problem that we did, we had y equal to 3x squared plus 1 squared. So we have an outside application, which is the square. And then on the inside, we have 3x squared plus 1. Whatever's on the inside, that's what we're going to call u. Hold on a second. I'm going to call that u, and then substitute u in for that middle piece. So u is 3x squared plus 1. If you were to plug in u here, that leaves us with y equal to u squared. All right. Taking the derivative of u with respect to x, taking the derivative of this with respect to x, that gives us 6x. Taking the derivative of this with respect to u gives us 2u. And then we have these two pieces here, derivative of u, and derivative of u and derivative of y. So you're taking the derivative of the inside and you're taking the derivative of the outside. So the inside took the derivative of this and then took the derivative of the outside. And so that's the way, like I said, I look at it. You take the derivative of what's on the inside of the application, and then you take the derivative of the actual outside. So that's 2u plus 6x. Put our u back in there, which is 3x plus 1. And then simplify the expression, and that's how we got 36x cubed plus 12x. All right. So, well, is anybody copying this before we go up to the next one? So that, like I said, that was from last class. Just did a little quick recap. And so we're taking that same type of thought process for the rest of the problems that we do in this section. So once again, you're taking the derivative of the inside and the derivative of the outside. So here we want to differentiate sine of x squared plus x. So once again, you have an inside, which is x squared plus x, and you have the outside application, which is sine. So we need to take the derivative of the inside and the derivative of sine, which is the outside. So I kind of broke it down the same way here. X squared plus x is the inside function. Sine is the outside function. All right. So instead of writing it all out like I did last time, this is the way we're looking at it. Like I said, if you want to write it out into pieces like we did in that first example, then you can. But here, sine of the outside function, the sine, derivative of the outside function, and then the derivative multiplied times the derivative of the inside function. So derivative of sine is cosine. And that's what this is here. This is right here, cosine of x squared plus x. We had sine of x squared plus x. Derivative of sine x squared plus x is cosine x squared plus x. And then derivative of x squared plus x is 2x plus 1. You bring your exponent down, subtract 1 from it. And then derivative of x as well is just 1. All right. questions on what we did there? It's the same thing that we did up here, you know, in that first example from last class. It's just that, you know, we didn't write down every single step. That thought process is you take the derivative of the outside function and then the derivative of the inside function and multiply it. All right, can we do another one? All right, same thing here. We have an inside function, which is 5x cubed minus x to the fourth. Outside function, which is the seventh power. So taking the derivative of the outside, which is the exponent of 7, you know, you bring your 7 down and then subtract 1 from it. So for that piece, what's on the inside stays the same, just like with this cosine x squared plus x, that part stays the same. And then you take the derivative of the inside. Take the derivative of the inside, and that's this right here. So you leave the 5 there, bring down the 3, and then subtract 1 from the 3. And then for the next one, you bring that 4 down, and then subtract 1 from that 3. Subtract 1 from the 4, and that gives you 3. Multiply these together, gives you 15. And that's it. Make sure we're okay.
Why did we subtract 1 from the 4?
That's just the process of the derivative of x to the fourth. We take the derivative of x to the fourth. You bring down the 4. So that'll be 4x, and then it's 4 minus 1.
Oh,
so the
right.
result
Okay.
be, All right. Anything else? Anybody else before we go to the next one? Make sure we're good. All right. So here we're taking the derivative of 1 over 3x minus 2. So that 3x minus 2 is in our denominator, so we could actually raise it up to the numerator by rewriting it with a negative exponent. So it's 3x minus 2 raised to the negative first power. All right. So we can do the same thing here now because of the way we've rewritten it with the problem that we did, the same way we did the problem previously. So bring down a -1, subtract 1 from it, and that'll give me -2 for the exponent. So that's the outside. Then take the derivative of the inside, which is just 3. So we're talking about this 3x minus 2, take the derivative of 3x minus 2. That'll give you 3. So if we want to rewrite this without the negative exponent, bring the 3x minus 2 down to your denominator. That negative is still here, and then that's 3 in your numerator. All right, problems before we look at another one. All right, so here we have sine to the 5th power of x. Well, sine x to the 5th power. So when you see it like this, it's not sine 5x, sine of 5x would be more so like that. But that's the 5th power. So I tried to write it the best way I could, but that's sine x to the 5th power. So both of these represent the same thing, whether you write, the fifth power right here, or if you write sine x raised to the fifth power, you can write it either way and still be fine. All right. So we can bring that, we recognize what we have here. Once again, we have an inside function, which is sine x, outside function, which is the fifth power. So the outside, bring the 5 down, subtract 1 from the 4. So that's the derivative of the outside. Derivative of the inside, derivative of sine is just cosine. So that's the answer there. Any problems? Any problems? So the chain rule, once again, you take the derivative of the outside, then take the derivative of the inside, multiplied by the derivative of the inside. Here's the next one. Tan of 5 minus sine, tan of 5 minus sine 2x. I say 2x, 2t, 2t. All right. So once again, we have an outside function, inside function. But then also, when you look at sine of 2t, you have sine, and then inside of sine, you have 2t. So we're going to have to look at this, apply the chain rule at least twice. So first thing we do is look at this outside function of tan. That's secant squared. So tan of 5 minus sine 2t is going to be secant squared of 5 minus 2t when you take the derivative. All right. So then we're looking at the derivative of this inside here. Now the derivative of 5 is just 0. Remember, the derivative of any constant is 0. So really we're just looking at the derivative of negative sine 2t. And like I mentioned, you have sine of 2t. So that means you have to take the derivative of sine and you have to take the derivative of 2t.
Mr. Tucker?
Mm-hmm.
I'm sorry, I'm confused. How did we go from the top to the secant squared?
Derivative of tan is secant squared.
Oh, okay.
Yeah, so that goes back just to our tan trig, derivative of our trig functions.
Right.
Yeah, so I know it's kind of funky, but that one goes straight to secant squared. Cosine goes to sine, sine goes to cosine, but tan goes to secant squared.
Okay, thank you.
Yeah, not a problem, not a problem. All right. So then looking at the derivative of sine 2t, because remember we had to take the derivative outside, which was tan, but then the derivative inside, which is 5 minus sine 2t. Once again, derivative of a constant is 0. So we're looking at the derivative of sine 2t. That is actually going to be derivative of sine, which is cosine 2t. Then since it's 2t in there, you have to take the derivative of 2t, which is just 2. So that's what we're looking at right here. Multiplied times the derivative, multiplied times 2 cosine 2t. And really could have put parentheses around that as well. Then just to bring it out front so you wouldn't have to use parentheses, wrote it this way. And all it is, like I said, just moving negative cosine 2t to the front. Make sure we're all right. All right. All right. Scroll up. All right. So the next one, derivative of 1 over 1 minus 2x to the third power. So that whole 1 minus 2x is being cubed there. So not just 1 minus, well, that's the quantity is being cubed. So just like before, we can rewrite it as 1 minus 2x to the negative third power. So we can take the derivative by using our regular process. So the negative third power is the outside, 1 minus 2x is the inside. So bring your negative 3 down. Don't forget you're going to subtract 1 from negative 3, but negative 3 minus 1 is actually negative 4. So be careful with that. Then take the derivative of the inside. So derivative of 1 is 0. Derivative of negative 2x, it would be negative 2. So to write it as a positive exponent, you can drop it back down to your denominator. And then multiply that negative 3 and negative 2, that'll give you a positive 6. Any problems? All right, let me go. Sorry, I was trying to get this thing straight on my computer. All right. Okay, let's see, let's get another one in there. Hold on, I pulled it up somewhere. All right, while I pull up this problem, anybody have any questions? Mm-mm. Mm-mm. Mm. Okay, it's right there. All right, so looking at the derivative of this one. Oh, let me do this. Don't forget this square root is the same thing as 1/2 as an exponent. So if I wanted to take derivative of this, don't forget, once again, no matter what the exponent is, first move is to bring it out front. So it's 1/2. And then we subtract 1 from it. So it means we'll have negative 1/2. All right. Then we have to take the derivative of the inside. So that's going to be 3. Bring out, that part of your that part of your term is not affected by the derivative. You bring that to the front and just do the derivative of x squared. So that'll be 2x. And then minus 4. And then the derivative of 6 is just 0. Derivative of any constant is 0. As a matter of fact, I can go ahead and bring that down bottom. All right, so that should be a negative exponent of 1/2. So since it's negative, to make it positive, bring it down bottom. Then we can simplify this as 6x minus 4. And we also can simplify this further, applying that 1/2. Since the 1/2 can go into the 6 and to the 4. When it comes to multiplication, if all of this multiplication, you can apply it in any order. So that'll be 3x minus 2, taking half of each one of those terms. And now, since this is a numerator, I can just multiply it. If we look at this as a fraction, 3x minus 2 over 1, just multiply it across. And that'll be 3x minus 2. Am I okay with scrolling up? And I can actually write that 3x squared minus 4x plus 6. Another radical. And that'll be that answer. All right. Questions before we do another one? All right. Get rid of these t's. It's not necessary. I'll use x. They use t, but I don't want my t's to get mixed up with nothing else. So we have x tan x raised to the 10th power. So we have our 10th power that's on the outside, x tan x on the inside. So bring down to 10. Subtract 1 from the exponent. So that's 9. Don't forget product rule. So if we're going to do the product rule, U is going to be X. V is going to be tan X. Derivative of U, which is X, is just going to be 1. Derivative of X is just 1. Derivative of V, secant squared X. So don't forget product rule is U V prime. I guess I could have just called that V prime instead of dV dx, but U, which is X, times V prime, which is sine, oh, not sine, secant squared X plus V times U prime. All right, make sure we're okay. All right, that should be good enough. I'm trying to see if there's anything else we can do with this problem. So secant squared is 1 minus, nope, then we have X. Yep, that should be it. All right, questions on that? Any problems or questions with the chain rule? Everybody good? Everybody straight? Let's see 3.7. See what's going on here. I think this is implicit differentiation. Yes. All right, so let's look at implicit differentiation. So we're looking at taking the derivative of an expression with respect to a different variable. All right. So it's almost like you're taking a partial derivative, kind of, sort of. All right. So what we mean by that, like if I was taking the derivative of x squared with respect to x, that's just going to be 2x. You know, you bring your derivative down, subtract 1 from the bring your exponent down, subtract 1 from that exponent. Same thing if I was taking the derivative of y squared with respect to y. Same result, it's just that we have a y instead of an x. Okay. So that's taking the derivative with respect to that variable. Like I said, we are looking at taking derivative with respect to a different variable. So if I had a derivative of y squared with respect to x, so you're going to take the derivative of that function with respect to it, and then what's going to be left is this this piece, the derivative of y, which is what we were taking the derivative of with respect to x. And that piece is always going to be left. So that was derivative of t squared with respect to x. Going to take the derivative of t squared with respect to t, and then that'll be the derivative of t with respect to x. And that piece is going to be left. Okay. And you'll see what I mean as we continue to go on. So notice how dy dx is still there because you cannot take the derivative of it fully when you're taking the derivative with respect to another variable. So this piece right here will still be left. All right. So a piece is always going to be left of the derivative. And that's the way I process it. A piece of the derivative will always be left there if you're taking it with respect to another variable. All right. So here, if you're taking the derivative of 5y cubed with respect to x, so once again, you're going to take a derivative of what you have with respect to that variable. So we'll take the derivative of 5y cubed with respect to y. And then you'll have this piece here, dy dx, derivative of y with respect to x. So bring down to 3, subtract 1 from the exponent, which is 2. That'll be y squared. Then 5 times 3 is 15y squared dy dx. Any problems so far? All right. So here it says find the slope of the circle x squared plus y squared equal to 25 at the point 3, -4. All right. So first you want to find the derivative of the equation. So we take the derivative of each piece with respect to x. Of course, if I scroll up and you still copying something, let me know. So the first one, derivative of x squared with respect to x, is just 2x. Then the derivative of y squared with respect to x is 2y, but it's the derivative of y squared with respect to x. So you're still going to have this piece left, dy dx. Then we have derivative of 25, a constant, which is 0. Derivative of a constant will always be 0. All right. Let's scroll up. Everybody okay? So now we can solve for dy dx. And we're talking about getting this piece by itself. So subtract 2x. All right, so subtracting 2x from both sides, that'll give you 2y dy dx minus 2x. Now, divide both sides by 2y. And that reduces to negative x over y. So derivative of y with respect to x ends up being negative x over y. All right, any questions so far? All right, so now we have the point. We can go ahead and substitute in 3, negative 4. Remember, taking the derivative of our function was how we found the slope before. Well, we used the difference quotient, and then we found out that the derivative took the place of the difference quotient. So that's what the derivative will do for us. And we can plug in the point that we have. Before, all we had was x that was left over, but this time we have x and y. Implicit differentiation sets us up to have x and y left over. So we go ahead and plug in the point 3, negative 4, 3 for x, negative 4 for y. And that simplifies to 3/4 as our slope. Questions. All right, can I roll up? All right, so taking implicit differentiation to the next step, it gives us a few steps that will help guide us on doing so. So we're going to differentiate both sides with respect to x. Collect the terms of dy dx on one side. Solve for dy dx, which is y prime, and that would be the derivative. So that would be implicit differentiation. Excuse me. All right, let me scroll up. So they're asking us to find dy dx if y squared is equal to x squared plus sine xy. So we take the derivative of each piece. All right, so implicitly, taking the derivative of y squared was that partial differentiation either way. Taking the derivative of y squared, that gives you 2y. But because we're taking it with respect to x, that leaves us with the dy dx piece. Taking the derivative of x squared will just be 2x. Then we have to take the derivative of sine xy. So don't forget that we will have to use a chain rule in that case. We take the derivative of sine xy, which is cosine xy. But then you got to take the derivative of the inside, which is just xy. And because we're taking the derivative of this, let me see how I will label this. Here we have to take the derivative. I got to use the chain rule. Here we need to take the derivative and use the product rule. One more time. No, I don't like that. All right. So we use the chain rule, and that's how we got this two pieces. Then we have to use the product rule, x times y. So that means you need to take the derivative of x and the derivative of y, and then multiply them to the x and y. So if I actually, let me do this since I put them in the, just trying to stay consistent, I put them in the other order. So I'll just do this. So x would be u. So that's u times v prime. So it's dy dx plus v, which is y, times x prime, which is just 1. All right. Make sure we're okay up to this point right here. So now at this point, we need to get our terms with dy dx on both sides of the equation. We need to distribute cosine to each term so that we can have access to that dy dx term. Of course, if I scroll up too far, let me know. So this is what we have. And I just leave it. Well, I guess since I wrote it in that order, I'll rewrite it. So it's x. Oh. So doing our distribution, that's 2x plus x cosine xy dy dx plus y cosine xy. So now we need to get this term over here, and we'll end up subtracting both terms. We're subtracting that term from both sides. Right, that's a little better. So these cancel here. And this is what we have. So And, without the boxes, of course, but we want to factor out dy dx. That's why we got all of our terms with dy dx to one side of the equation. All right. So like I said, we want to get dy dx to the outside. So factor both of those out. That leaves 2y minus x times cosine xy in the parentheses. Then we can go ahead and solve for dy dx by dividing both sides by that quantity of 2y minus x cosine xy. So that they cancel out. Any problems? Any problems? And that would be our answer. So 2x plus y cosine xy over 2y minus x cosine xy. All right, any problems? Let's see, we got this one. I think that's the last one I got. Oh, got this one. Okay, cool. All right, here. So here we're looking at taking the second derivative of 2x cubed minus 3x squared equal to 8. So just like before, we take the derivative of each piece with respect to x. So 2x cubed, bring down to 3, and subtract 1 from the exponent. So that's 2 times 3x squared minus the derivative of 3y squared. So take the derivative of y, bring down to 2, subtract 1 from your exponent. So 3 times 2y. And don't forget, we're taking that with respect to x. So there still should be that dy dx still attached to it. And then the derivative of 8 is 0. Of course, the derivative of any constant is going to be 0. So we're here with our simplification. 6x squared minus 6y dy dx equal to 0. All right, so now we can solve that for dy dx. Subtract 6x squared from both sides. Then divide by 6y. There should be a minus sign right here. All right. So dy dx is equal to x squared over y. Once we simplify this right here. All right, so now we have to take the derivative again, because remember we need the second derivative. Mhm. Hold on 1 second. All right, so I was just writing down. I think somebody asked me, something about notation, but y prime, same thing, of course, is dy dx. So we were looking for y double prime, or in other words, the second derivative. So we have to take the derivative of what we had, which is x squared minus one, x squared over y. So we can use the quotient rule. So we let u be x squared, u prime would be 2x then, v would be y, derivative of y is just dy dx. All right, so plug in your pieces. We have y times 2x minus x squared times dy dx over y squared. And just plugging it in according to the quotient rule. All right. Now we can simplify this a little. See, we ain't really, well, I guess it was okay to do that. So simplify this a little. Didn't necessarily have to because we weren't finished yet, but I guess we wanted to separate it. That's fine. Okay, it must be in the book, what the book was looking for. So separating this by taking y squared into each term. And that'll be 2xy over y squared minus x squared times y prime. So don't forget the derivative of dy dx is same thing as y prime. So I was just writing it shorthand there. That's over x squared. And then this square and one of these x's will cancel. And so that would be 2x over y minus x squared over y squared times y prime. And we almost finished. All right. So to get rid of that y prime, remember we already had y prime. which was x squared over y. We can go ahead and substitute that back in. Not back in, just substitute it in. And that'll be x squared over y for y prime. Once again, if I scroll up too far, let me know. And that'll be 2x over y minus x to the fourth over y cubed. Hold on. All right, all right. Everybody good? We got one more down here. Is everybody good with what we've done up to this point? Make sure we're good. I know some questions may not come up until you actually try this stuff out. All right. So last problem for today, we have find the tangent to the curve x cubed plus y cubed minus 9xy equal to 0. And it's at the point 2, 4. All right. So once again, first move is to take the derivative of the whole equation, each piece. Amazon man there was like, who's at my door? Derivative of x cubed is just 3x squared. Bring the 3 down, subtract 1 from the exponent. Derivative of y cubed, bring your 3 down, subtract 1 from the exponent, 3y squared. But once again, we're taking the derivative of y with respect to x, so there still should be this dy dx piece still there. Then taking the derivative of 9xy. And here, once again, we have to make sure we hold true to the product rule. So take the derivative of x and the derivative of y. So that's why we have u v prime. So that's x dy dx. And then v, which is u, derivative of x is 1. Is better. All right, any problems? I didn't mention it, but of course, derivative of 0 is 0. So now our goal is to get all of our terms with dy dx to one side of the equation, each one of our terms without dy dx to the other side. So since we had that other side that have 0 to it, I'm going to subtract 3x squared and add 9y to both sides so that they will cancel out for us on the left and just be on the right. All right, any problems? So this is what we have now. 3y squared dy dx minus 9x dy dx equal to negative 3x squared plus 9y. All right. Factor out dy dx. We got room for it. Nope, didn't make room for it. So factor out dy dx. And then divide both sides by 3y squared minus 9x. So that'll cancel out on the left. And this is what we have now. So we have 3x squared, negative 3x squared plus 9y over 3y squared minus 9x. And I think we're looking for the tangent line. I forgot what we're looking for. Yep, tangent to the curve. Didn't know if we were just looking for the slope or not. So I just decided to simplify this further by factoring out 3 from each term and canceling them out. So it gave us negative x squared plus 3y over y squared minus 3x. So we have that point of 2, 4 that they gave us. So we can substitute that now into the equation, or into our derivative. 2 for x, 4 for y. So this is just another way of notating that. Just that means plug in 2 and 4 into the derivative. So just notation. So then down bottom, 4 squared minus 3 times 2. So that's negative 4 plus 12, 16 minus 6. 8 over 10 is 4/5. Any problems? Make sure we're good. All right, so don't forget that's our slope. And now we can use the point slope formula to find the tangent line. All right. So y14, x12, m is 4/5. Plug it in accordingly. Y minus 4 equal to 4/5 times x minus 2. Distribute that 4/5. That'll be 4/5 x minus 8/5. Add 4 to both sides. So then we just have y on the left. And then 4 plus negative 8/5. You know, in order to have add or subtract your fractions, need a common denominator. So that 4 is 4/1. Multiply top bottom by 5. So we have a denominator of 5. That's 20/5. Negative 8/5 plus 20/5 will be 12/5. And this is our equation. Y equal to 4/5 x plus 12/5. All right, questions. All right, let's see. Yep, that's it for that one. So that's it for lecture today. That was 3.6 and 3.7. Questions on anything? Next class, once again, I'll open the floor for questions first, just in case some are generated over the weekend. If you have questions and fill up class time, then that's fine. We don't necessarily have to do anything new next class, but the floor will be open for you guys to ask whatever you want to ask first before we do anything else. All right. Any questions before we close out today? Is everybody good? Everybody straight? All right. So you guys have a good one. Have a great weekend. Be safe. And I'll see you on Monday.